Yeah, welcome to pre-calculus class. We're going to start section 4.5, which is sketching graphs of sine and cosine functions. Okay, so let's look at sine first of all. So we've been calling sine a function, but we haven't really treated it like a function yet. But if you need to think of it like a function, where if you put in some value in for x, then you're going to get some output value of y, okay? And, you know, in most cases for us for now, the x values we're gonna put in are going to be places that we have already learned how to evaluate on the unit circle, okay? And then the y values are going to be whatever the corresponding y values are. So you can take that and you can make a graph, okay? And it's helpful, you know, when you make your graph. So your y values are going to be not integers necessarily, but they're going to be regular kind of numbers, whereas your x values are going to be radians, okay? So I'm going to start with one period. Remember we said that the period of sine was 2 pi because it repeats itself every 2 pi. So I'm going to mark 2 pi out here. I'm going to go about halfway, and I'm going to make that pi, and then half of that is pi over 2, and half in between here is 3 pi over 2, and I could put maybe another point over here, negative pi over 2, and then maybe a negative pi here, okay? So these are our x values that we're going to evaluate. So let's look at a table of values. Remember when we first started graphing functions in this class, one way that we could always do it was to make a table of values. So we're gonna do that here. So we're gonna have x, and then we're gonna have sine x. All right. And I'm gonna start at 0. Okay. So the sine of 0 is 0. The sine of pi over 2 is 1. Okay. The sine of pi is 0 again. The sine of 3 pi over 2, okay, is going to be negative 1. And the sine of 2 pi is going to be 0 again. So we can put that onto a graph, okay? So at 0, our sine is 0, okay? We make this 1. At pi over 2, the sine of pi over 2 is 1, so it comes up here. And then at pi, it's 0 again. And then at 3 pi over 2, it's negative 1. And then at 2 pi, it's back to 0. Okay, now you could, remember that the domain of sine is all real numbers. So you could really put any number into sine and you would get a value, all right? In general, when we are graphing trigonometric functions, I am going to ask for 2 full periods in the graph. For now, we're just going to look at this right here. Now, the sine of negative pi over 2, it would be the same as the sine of 3 pi over 2. So it would be actually negative 1, and then the sine of negative pi would be 0 again. So our sketch is going to look kind of like this. All right, and then it just keeps going and going and going. So that's a basic sine graph. You know, one period would be from 0 to 2 pi. Okay. The domain of sine, as you know, is all real numbers, I just said. Okay. And then the range, which we talked about, but look at it, okay, from negative 1 to 1, okay, it goes, you know, from negative 1 up to 1, then back down and back. So the range, and it includes those points, so the range is from negative 1 to 1. Okay. Now from 0 over to 2 pi, that is one period. All right. Now I want to look at cosine. Okay. Y equals cosine x. Okay. And we can make a table. Okay. So we've got x and we've got cosine x. And we're going to look at 0, pi over 2, pi, the same points we looked at for sine, and 2 pi. So the cosine of 0, I hope you remember, is 1. The cosine of pi over 2 is 0. The cosine of pi is negative 1. Of 3 pi over 2 is 0 again, and of 2 pi, it's 1 again. So if I want to make a graph, once again, I'm going to do 1 period for now. So we're going to go out to 2 pi. Half of that would be pi. Half of that would be pi over 2. And in between here, you've got 3 pi over 2. You've got 0 here, maybe a negative pi over 2. Okay, this would be 1, and this would be negative 1. Okay? Maybe it'll be up a little bit from there, maybe right around here. Okay? Try to keep things even. Okay? So at 0, cosine is 1, so it's right here. Okay? At pi over 2, it's 0. At pi, it's negative 1. Okay? At 3 pi over 2, it's back to 0. And then at 2 pi, it's 1 again. All right? And if I wanted to extend it to negative pi over 2, that would be 0 also. So our cosine graph looks like this. So it looks just like the sine graph, but it's a shift. Okay? Sine starts at the intercept, goes up, and then back to the intercept, then down, then back to the intercept, whereas cosine is going to start at 0 at its maximum and go through the intercept down to the minimum, then to the intercept again, and back to the maximum. Okay? And once again, 1 period would be from 0 to 2 pi. Okay? And it's going to be very important when we look at sine and cosine graphs that we distinguish some key points, okay? Because we're going to use those key points over and over again, okay? To help us with transformations of these functions, of these graphs and all that. And the key points for sine are right here, and the key points for cosine are right here. So your key points, okay, for sine would be 0, 0, which is an intercept, would be pi over 2 and 1, which is a maximum. Notice it's at the max. Okay, and then pi and back to 0, which is another intercept. And then 3 pi over 2 and negative 1, so we have a minimum. And then finally down here, 2 pi and 0, which is another intercept. Okay? So those are your key points for y equals sine x. Okay, your key points for y equals cosine x. We're going to use the same x values, but as you can see, they have different y values. Okay, so our first one is going to be 0, 1. That's going to be a maximum. The next one is going to be pi over 2 and 0, which is going to be an intercept. Okay, and then we would have pi and negative 1, which is a minimum, followed by 3 pi over 2 and 0, which is another intercept. And finally, 2 pi, and we're back up to the maximum at 1. So these are your graphs of sine and of cosine, okay? Notice that, as I said before, the cosine is just a shift, okay? Basically pi over 2 to the left of sine. So we're going to be spending a lot of time looking at transformations of trigonometric functions, and since we're talking about sine and cosine, we're going to start with that. And a lot of times when we do this, when we sketch something with a transformation, we're going to use those key points that I was talking about. So let's look at example 1, which is titled Using Key Points. Okay, so, and we're going to sketch a graph of y equals 2 sine x. Okay, so remember your x values for your key points were the same for sine and cosine. They were 0, pi over 2. Sorry, this should be 2 sine x. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay? But when we change it to 2 sine x instead of sine x, we're gonna, the x values are gonna be the same, but the y values are gonna change, okay? The input is the same, the output is different. So remember that the sine of 0 is 0, so this is really gonna be 2 times 0, which is still 0, okay? When it's pi over 2, the sine of pi over 2 is 1, so this is going to be 2 times 1, so it's going to be 2. Sine of pi is 0, so 2 times 0 is 0. Sine of 3 pi over 2 is negative 1, so it's going to be negative 2. And the sine of 2 pi is 0 again, so 2 times 0 is 0. Okay, so we use those initial key points to get new. We use the x values of the key points to get new y values. And then when we go to sketch the graph, okay, we're going to look at one period again. Okay, so half is pi, and pi over 2, and 3 pi over 2. Okay, and if I make this 1 and 2, okay, one thing to keep in mind when you sketch these graphs is that the x-axis and the y-axis are independent as far as scale, okay? So if this is 1 and this is pi over 2, now pi over 2 is closer to 1.5, but they look the same as far as distance, but that's fine. What you need is consistency on each axis. So if the distance from here to here is pi over 2, then the distance from here to here also needs to be pi over 2. And I'll be checking that. Not exactly, but it's got to look right, okay? And then also, if this is 1, then this is 2, and this is negative 1, and this is negative 2. So you need to be consistent on each axis, but the axes can be independent of each other as far as scale, okay? So our first point is going to be 0, 0, okay? Then our next point is going to be pi over 2 and 2, okay? Then we're going to have pi and 0. Then we're going to have 3 pi over 2 and negative 2. And then we're going to have 2 pi 0. You may notice that this actually looks a lot like the graph of sine x that I did. And that's because I changed the scale, okay? Whereas when I did sine x, I might have made, you know, this 1, but now I'm making it 2. So you could end up where your graphs of all these different transformations look very similar, okay? But what's important is the markings, okay? And when you sketch graphs of sine, cosine, any trig functions, I'm always going to want you to take the period and to divide it into 4 sections. So there'll always be 5 points for one period, okay? So that, that's the level of accuracy that I'm going to require of you. So this is y equals 2 sine x, and we graphed it using key points. Now, this number here, 2, is something that we're going to call the amplitude, and I'm going to get into that in a second. But before I do that, in general, I want to talk about, you know, how we're going to transform sine and cosine functions, okay? So, transformations of sine and cosine functions. I'm going to start you with a general sort of formula for a sine and a cosine function. So this is y equals d plus a sine of bx minus c. okay? That would be a general form of a sine function and the general form of a cosine function, d plus a cosine bx minus c. And each one of these letters, okay, I mean, x is still the input, right? But each one of these other letters, the d, the a, the b, and the c, or the a, the b, the d, and the c, or whatever order you want to say it in, is going to do something else, just like it did with other functions, okay? So there were general rules for transformations of functions that we learned with polynomials, we learned them with logarithmic functions and exponential functions and every other kind of function, and it's going to be true with trigonometric functions as well. So if you recall D, let's look at A first of all, okay? Now notice here, this is y equals 2 sine x, okay? And what did it do? Well, it stretched the y. It increased the y value up and it increased it down, the same amount on either side, right? So it's like stretching it. It's a vertical stretch, okay? And if you recall from other functions, if you had some number that you multiplied outside of the function, if that number was greater than 1, then it would, if the absolute value of that number was greater than 1, then it would be a vertical stretch, all right? And it's the same thing here. So we're going to say that A is a scale factor, okay? And it produces a vertical stretch or shrink. Ignore that, okay? When we get to B, B is actually going to be a change in period, okay? It's another scale factor, but remember that, so when we had the scale factor with other functions that was inside of the function, okay, then that was actually a horizontal stretch or shrink, okay? And it's going to be the same with these. So it's going to be a scale factor as well, but it's going to be a horizontal stretch or shrink. And that's going to change the period, all right? C, remember if you had x minus 2 squared, right? X minus 2 squared would take the parabola x squared and it would move it 2 to the right, okay? Well, we have a minus c inside of here, so that's going to be a horizontal shift, okay? So that is a horizontal shift, just like it was for other functions. And finally, D, remember if you had x squared plus 1 with the 1 outside, okay, you were just shifting everything up 1. So same thing here. It's a vertical shift, okay? So all of these letters have meaning, and we're going to learn how to use them to sketch graphs of sine and cosine functions, okay? I want to start by looking at A, okay? Come over here. Now we have an A here, right? In this case, A is 2, all right? And you can see that then the maximum, originally the maximum of y equals sine x was 1, well now it's 2. And the minimum is now negative 2 instead of negative 1, okay? So in general, when the absolute value of A is greater than 1, we're going to have a vertical stretch. And when the absolute value of A is between 0 and 1, so when A is a fraction, okay, then we're going to have a vertical shrink. And it makes sense that it would shrink, right? Because if it was 1/2 sine x, then each of these would be multiplied by 1/2. So instead of 1, you'd have 1/2. Instead of negative 1, you'd have negative 1/2, okay? So it would be shrunk vertically, okay? And A is going to change the range of your function. So the range of y equals a sine x and y equals b sine x is, I'm sorry, a cosine x, is the range of y equals a sine x and a cosine x is actually going to be dependent on a. So it is actually from negative a to a, including those endpoints, okay, instead of the original of negative 1 to 1, okay? Now, I want to define a. We're going to say, actually, I'm defining the absolute value of a. We're going to say the absolute value of a is the amplitude of y equals sine x and y equals cosine x. I'm sorry, of y equals a sine x and y equals a cosine x. Okay, that's the amplitude, all right? And the definition of amplitude is the amplitude of y equals a sine x and y equals a cosine x represents 1/2 the distance okay? It's 1/2 the distance between maximum and minimum values. Okay, so if you had, you know, a function that went up and down like that, the amplitude is 1/2 of the distance from here to here. Okay, that's the amplitude. It's the absolute value of a. Okay? So amplitude equals the absolute value of a. So let's look at a couple examples of amplitude with cosine. Okay. So example 2. I'm going to graph 2 functions on the same graph so you can see how they're different, all right? So for a, our function is going to be y equals 1/2 cosine x. Okay, so we can still start with our key points, right? So you got x, you got cosine x. You can always do this. I'm sorry, you don't have cosine x, do you? You've got 1/2 cosine x. You can always work this way, all right? So you've got 0, pi over 2, same key points. Pi, 3 pi over 2, 2 pi, okay? And it's going to be 1/2 times the cosine of 0, which is 1. So that gives us 1/2. Then it's going to be 1/2 times the cosine of pi over 2, which is 0, so it's going to be 0. Then 1/2 times the cosine of pi, which is -1, so it's -1/2. And then 1/2 times the cosine of 3 pi over 2, which is 0, so it's 0. And we end up with 1/2 times 1, the cosine of 2 pi, so it's 1/2. Okay? So my graph okay, here's 2 pi, here's pi. One hint for drawing these, you know, if you're using graph paper, it's not an issue, but if you're just using regular line paper or blank paper, and you're having difficulty keeping the spacing, do what I do. Start out at the end of what you want to graph, cut it in half, okay? Then cut it in half again. It's a lot easier, that way you don't start drifting, okay? So it's easier if you start out at the end and you just start by cutting things in half. So I'm actually going to make my y-axis a little bit longer because I'm going to put a couple graphs on here, and one's going to have a higher amplitude. So I'm going to make this 1, 2, and 3, and -1, -2, and -3. Okay? So for our graph of 1/2 cosine x, a half is here. Okay? So we start here. And that's because it's 0, 1/2. And then it goes to pi over 2, 0. And then it goes to pi 1/2, -1/2. Okay, then it goes back to 0, and then back to 1/2. So the graph would look like this. Okay? So that's a vertical shrink that we have because the amplitude is between 0 and 1. Okay, and then I also want to look at the graph of 3 cosine x. Okay, so same key points, 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, and it's going to be 3 times 1, which is 3, and then it's going to be 3 times 0, which is 0, and then it's going to be 3 times -1, which is -3, then it's going to be 3 times 0, which is 0, and then it's going to be 3 times 1 again, which is 3. Okay? So I'm going to start up here, then I'm going to go to here, then I'm going to go to here, then back up to here. Okay? So it's going to look like this. All right? So you can see the amplitude has changed, how the graph looks. All right? So that would be graphs of y equals 1/2 cosine x and y equals 3 cosine x. Okay? Now I want to look at one other graph of cosine with an amplitude change, and that's going to be if we have if the value of a is negative. Okay, so I haven't really talked about that. Now remember, the amplitude is the absolute value of a. So if a is a negative number, the amplitude doesn't change because a is negative, but the graph is going to be different. So I want to look at y equals -3 cosine x. Okay, so for -3 cosine x, we can start with our key points again, x and -3 cosine x. Okay, and 0 and pi over 2 and pi and 3 pi over 2 and 2 pi. Okay, so this is going to be -3 times the cosine of 0, which is 1, so it's -3. Then it's going to be -3 times 0, then -3 times -1, which is +3, and then -3 times 0, and then -3 times 1 again. So how is this going to look different? Well, it's going to look different because of where it starts and where it ends. Okay, so if I make this 3 up here, and if I make this -3 down here, okay, and I'll make this 2 pi, and pi over 2, I'm sorry, and pi, and then pi over 2, and 3 pi over 2, okay? So I'm going to start down here. I'm starting at -3, then I'm going to 0, then I'm going to 3, then I'm going to 0 again, and then I'm back down to -3. So instead of looking sort of like a U, all right, it now is going to have more of a bell shape. Or I could say instead of looking like an upside down bell, it's going to look like a right side up bell. All right? So now think about this. When we talked about transformations of functions in the past, we said that -f of x was an x-axis reflection. Okay? And that's exactly what happened here. This just reflected over the x-axis. Okay? Now, I want to talk about period of sine and cosine functions. I'm going to give you a minute to get all this stuff written down, and then we'll be back. Okay? All right, so I want to talk about period, okay, of sine and cosine functions. So we've already mentioned that the period of sine and cosine in general, just y equals sine x or y equals cosine x, is 2 pi, okay? But what we need to look at is our changes in period, transformations that cause a change in period. And as I said, that was when we have something in the form of y equals a sine bx, or y equals a cosine bx, okay? The b is going to be the change in period. That's also going to be true if it is bx minus c, where there's some horizontal shift. But for now, I just want to look at the b, okay? So these are going to be changes in period. So what we're going to say is we're going to say let b be a positive real number the period of y equals a sine bx and y equals a cosine bx is given by period equals 2 pi divided by b, because you're starting, originally you have a period of 2 pi. So if you have some number multiplied by x in here, if you divide the original period by that number, you're going to get a new period, okay? And in particular, okay, when b is between 0 and 1, so some fraction, all right, then the period is greater than 2 pi. So think about it, you know, if you divide by a small number, then you get a larger result, right? If you divide by half, that's the same as multiplying by 2. So if your period is between 0 and 1, then you're actually you're increasing the period beyond 2 pi, okay? Sort of opposite of the way you would think it would be. And then if when b is greater than 1, okay, the period is less than 2 pi. Okay? So this here is a horizontal stretch. And this would be a horizontal shrink. And that fits with what we've learned about functions in general in the past, okay? As far as horizontal, what stretches and what shrinks horizontally. So let's look at an example, all right? And with this example, I'm going to show you a little trick that's going to help you, you know, to sketch graphs of all these trig functions, which is we're going to use key points to get new points, okay? Which we've sort of been doing already. So take a second, write this down, and then we're going to look at example 3, okay? You can pause me if you want. I'm going to erase this. Okay, so example 3. We're going to look at the function y equals sine of x over 2. Okay? So, first of all, the amplitude for this is just 1. Okay? Because there's no a there. All right? And the period is going to be 2 pi. Now be careful, it's not 2 pi over 2. This is the same, x over 2 is equal to 1/2 x. okay? So the period is 2 pi over a half, okay? So that means it's actually 4 pi, all right? So right away, right off the bat, we know that we're going to be looking at, if we're graphing one period, we're going to be looking at a period of 4 pi. So I'm going to set myself up by going out to 4 pi instead of out to 2 pi, okay? And so then half of that would be 2 pi, and half of that would be pi, and half of that would be 3 pi, or halfway between, right? So this is really all you really need to know, but I want to show you sort of a little trick. And when things get complicated with periods, when you start combining horizontal shifts and period changes together, it can get very complicated. So one technique is to take each x value from the key points and set it equal to this new value, x over 2, and then you're going to get a new point, okay? So you're going to make new key points. Which is just going to be fantastic, okay? So our first x value for our first key point was always 0. So what we do is we set 0 equal to x over 2, because our new first key point, okay, remember the first point from sine was always an intercept. So that first intercept is going to be at whatever x value makes this true, okay? Well, guess what? It's still, x still equals 0, okay? And so we're going to be looking at y equals sine of 0, which is still 0. So we still are starting at the point 0, 0. So that's nice. Okay, the next one, we're going to take pi over 2, which is our second x value for a key point, and we're going to set that equal to x over 2. Well, that would mean that x equals pi. So that's our second key point is going to be pi, and then the sine of pi over 2 is equal to 1. Okay? Then our next key point was pi, and we set that equal to x over 2. So that would mean with cross multiplication that x equals 2 pi. So that's our new point. That's the next intercept. So it's going to be 2 pi and 0. Okay? Then we would have 3 pi over 2 equals x over 2. So those 2's would cancel, and you would get x equals 3 pi. So now we would have 3 pi, okay? And sine of 3 pi over 2 is negative 1. So that's our next point. And then finally, if we go 2 pi equals x over 2, well, with cross multiplication, x would equal 4 pi, okay? So that would mean that this is 4 pi and then back to 0 again. So I used my original x values for key points, and I set them equal to the x over 2, and that gave me new key points. Now, because there's no horizontal shift here, there's only a period change, you don't have to go through all that for this. Remember, because I found out that the period was 4 pi, I could just start out here at 4 pi and divide it into 4 equal sections, and that's going to tell me what my key points, where my key points are at anyway, okay? So if this is 1, and this is negative 1, we start at 0, we go to 1, we go to 0, we go to negative 1, we go to 0. So here's my graph. Voila, okay? So that's graphing a period change, right? Notice it looks just like the graph of sine x. I've just changed these numbers, really, okay? And that's a lot of what you're going to be doing. You're going to end up with graphs that look the same, but the numbers are going to be different. And when I go to grade your graphs, I'm going to be looking at what the numbers are, okay? Not what it looks like, although they do have to look good.